In the meantime, a very simple, stupid question by me.
Yeah.
At a certain point, you said that with 58 qubits, it is possible to memorize a very big number of numbers. And if you can give us an idea of how to measure the relation between the number of qubits of a quantum computer and the number of numbers that it is possible to memorize, which is how it is possible to make this calculation. Okay, thank you.
I will share again the slides. Sorry.
Thank you.
So can you see the slides?
Not yet.
No. Not yet. So I have to just a moment to share again. I have to share again because I unshared my screen. So now. I'm sorry. This is the app that say that my time is over. Now.
Now, yes, we see your screen.
Yeah.
Not yet. Okay. Now we can see your slides.
Yeah. And you see here just a moment because it's not so easy to go to the
yes. Find
sorry. No. Here.
No, before I think.
I'm now. I find a better way to. Okay, here. Now I am. Okay. Sorry. This is the classical part. It's bit qubit. Okay. Now. Okay. So this is the computational basis.
Yes.
So you have. If you have N1, you have you live in C2, so you have two possible. You can in parallel you have only two numbers, the amplitudes of cat0 and cat1.
Sure.
If you have N2, then you have four possibilities in parallel, and so on and so on. So you have two to the n possibilities, and here. In the case of our huge numbers, you have 2 to the 53 possibilities of stocking in parallel exact information. That is classical registers. This
is only the power of 2. No, there is. Okay, there is no other trick. Only the power of 2. Okay.
Yeah. It's simply that. Yeah.
Okay. So, okay. Thank you very much.
Usually they are equi-prepared. For example, in the bidimensional case, you take 1 square root of 2. You take this 1 square of the n of the dimension in order to have equi-superposed states. Yeah, this is
okay. Understood. Thank you very much. Michael, I have a small question. Please, Michael.
Yeah, I would like to see you because I prefer so.
Yes, Michael. It is better when one poses a question. It is better to switch on both the camera and microphone, and after switch off. Okay.
Thank you, Roberto. That was a great talk.
Thank you.
I just have a small question. One slide towards the beginning. And throughout the talk, you mentioned the word parallelism a few times.
Yeah.
And I think the first time you mentioned it, you conjoined it with the word epistemic. It was like an epistemic kind of parallelism, and I just was wondering if you could expand on what that means.
Yeah. This is a possible interpretation because epistemic interpretation is that if you start from the very beginning that a state represent an information, a knowledge about a quantum system, then the epistemic meaning of such a quantum system is that you have a knowledge of probability squares model of C2 that a system might be true. The probability square model of C0 that information encoded by the state might be false. This is the epistemic content of and this happens at the same time, and it happens at the same time. So is it possible? And Marisa will talk about this interpretation and see how you can apply it. This is maybe one of the main tools we used for our quantum mechanics without quantum word philosophy. That is the application of the formalism of quantum mechanics outside the micro world. Just because the interpretation is that an epistemic state, if you understand it as in an epistemic way, can be used also for situation in which you have knowledge, distinct knowledge encoded in parallel, but also outside the physical domain. So it's an interpretation.
Thank you.
Thank you.
Okay. I make another silly question. My idea is that making very silly question encourage people to make other question, because it's very easy to make silly. So perhaps I do not pay sufficient enough attention. At a certain point, you said that with Toffoli gate and the Hadamard gate, it is approximately possible to make all. Why approximately and not completely? You can say something.
There is just a mathematical reason. It's a pure mathematical reason, because unlike the classical case, quantum gates are unitary operators, are quantum gates, and the set of quantum gates, unitary operators, is uncountable.
Sure.
So, being uncountable, by cardinality reason, there is no possibility to have a finite set of quantum gates in such a way that you can express in an analytic way, by means of a convenient sequence of this set of gates, the other set. It's just by cardinality reasons.
Yes.
It's a mathematical.
This theorem about the cardinality of the dimension Hilbert space, that you can approximate all the wave function with a numerable Hilbert space, but it is always an approximation, because wave function lives normally in a not always, but many kind of wave function lives on a continuum basis. Okay.
And this is all we need, of course.
Yes.
But as logicians, we are not completely satisfied, of course.
Yes.
Because we are familiar, maybe we are accustomed, or we are biased, maybe, by the classical case. So we have where we have the functional, the analytic, the universal functional universality. But now we have to think about possible logics based on finite, on an approximate set, universal set. So Toffoli and Hadamard are really interested, because are the two phases you need. Classical, one gate quantum, and then you have in approximate all quantum computation. And then we can develop a logic based on Hadamard and Toffoli, which is not the logic of quantum computation as it happens in the classical case, because these two gates only approximate the other gates, not function.
Okay. We arrived at the correct moment at the end of your conference. It is 10 minutes before 5 p.m. and so we can make a coffee break of 20 minutes. I remember to you that it is possible through Slack to make conversation. it is possible also to say.
Sorry.
Sorry?
There are 2 questions on the chat.
I cannot read.
Maria and
Sorry.
Patricia.
Okay, sorry. I didn't see because I was okay. Sorry. Clarissa, no.
Patricia
No.
and Maria.
Also,
First, Maria Oikonomidi and then Patricia Contreras Tejada.
Okay.
Please,
Sorry,
Maria.
I was not able to see because I don't scroll my mouse. Sorry. Okay, we can. Perhaps it's better to do now, Roberto. After
Yes. Yes.
Okay. We can begin with Maria. Sorry for my disattention. Maria, you can pose your question.
Can you hear me?
Yeah.
Yes.
So, if I remember correctly, you said there is a particle that is designed to have reduced sensitivity in charge noise, right?
Yeah.
Was it a photon? I don't remember which.
Transmons. They are called transmons.
Transmons. And what is the charge noise? What does that mean?
It doesn't mean that when these are very cold. Of course, they are superconducting in these computers, so are very, very cold. And by superconductivity reason, you have a charge move through a material without resistance. So this is the reason why these are based on transmons, and they stay at a very, very, very cold temperature near the absolute zero. So yeah, but they are not perfect. This is the reason why they are called they are called noise intermediate, because there is still a noise in the computation. This is why you see the results of the experiment are very not very stable. You see, today I was lucky, and I have also 50% of probability because the Melbourne quantum computer was in a good shape today, maybe, but not yesterday. And so there is some because there is noise. There is still noise, and but I think this is the trendy way now. Is not photons, photon computers, no electronic, but these artificial atoms, because they are not atoms in the very definition. They are made atoms just because they are in a superconductivity material.
I see now. Yeah, makes sense. Thank you.
Patricia, please.
Oh, sure. I did say that. I mean, I don't want to eat up too much time with the coffee break, but anyway.
No problem. It is my fault because I was not able to see your.
Don't worry. Yeah, so coming back to the question before about the epistemic states, so the thinking of a qubit as the epistemic state that stocks information in some way, right? I'm guessing that that's just one way of thinking about that, right? That that the fact that you said that is just a useful tool for then building up the quantum logic, whatever, it doesn't commit you to such an epistemic interpretation.
Right.
Okay.
Right. It's just an interpretation. I remarked several times. You can completely disagree about the interpretation, and the quantum, as we will see, the quantum logic, the logic of quantum computation still works, still runs. Okay, just a possible interpretation. Yeah,
sure. Cool.
It's something superimposed to the thing. Yeah,
sure.
Yeah.
Okay, Thibaut, it's your moment, please.
Yes. Do you hear me?
Yeah.
Yes.
Yeah.
Okay, so it's maybe just a naive question of terminology, but if I remember well, you talked about the superposition of states in the qubit as simultaneous storage of informations. But since the superpositions is always destroyed by measurement, is it correct to talk about storage or memory? Because we cannot exploit this superposition as a storage, as a classical storage.
Right. You're perfectly right. This is otherwise is the price you have to pay, because if you want to have parallelism, you have to pay to pay a price, and of course you cannot have parallelism, quantum parallelism, at the same time knowing exactly the state, and you need measurement, and when you measure, you destroy the superposition. It's a balance. It's a compromise.
Okay, thanks.
Clarissa, please.
Oh.
Okay, I just hope I will get kicked out. I can't turn on the camera because if I do, I may really get bounced out. I was bounced out just now. My question actually has to do with the reduced. Oops, I lost my question.
Reduced state.
It was actually on reduced states. I was just curious, or maybe I missed what you were saying about it. I mean, why do we need reduced Bell states? Why not just Bell states? And does that has to do with the Toffoli gate? And yeah, I'm just curious, you know, as to what you mean by these.
Could you repeat the last part of your questions after the reduced states, please?
Okay, I'm just wondering why we need reduced Bell states. You're talking about that in relation to the Toffoli gates.
Yeah.
And how different is this from non-reduced Bell states? I mean, does the Bell state as it is, I mean, is it efficient? I mean, does it operate in a Toffoli gate? Because I'm still trying to really understand how this Toffoli gate works.
Yeah, I need to reduce, because you apply to the main difference. I mean, unlike the classical case, our input now of our conjunction is a state of a composite system. Okay, the Bell state, and then you have two. You know that you have two components because it's a state of a composite systems, but so you apply you apply this conjunction to the global information composed by two. You only know that the information is composed by two parts, but you don't know which part you are referring. You know the part you are referring only when you take into account the reduced state, the subsystem, as usually in physics. When you have a system, which is you have to measure on a subsystem. And when in that case, you obtain the reduced state is a mixture. So it doesn't depend on.
Okay.
Yeah. So first you apply Toffoli to this global information. You know that your information is composed by two parts. You know that but you don't know exactly these two parts, as in the classical case. You don't know the conjuncts in an exact way. You know that there are two parts in these states. Then you apply the conjunction. Then you want to know which is the information by measuring on each subsystem, and then you have a reduced, and then you have a mixed state. So at the end, you find that the results of the conjunction is something completely different from what expect in a classical way. In other terms, is not the composition, is not a tensor product of the reduced state of the conjunct, of the real conjunct. So this is the.
Okay, so it's a necessity of superposition, what you were referring to in terms of the Schrödinger equation earlier.
Yeah.
Okay, thank you.
Thank you.
Okay. There is another question by Hugo. Please, perhaps it's better now, and we are a bit in late, but no problem. Hugo, please. Okay, sure. Go.
Can you see me?
Yes. Yeah. Go ahead.
So I come at this from kind of a quite new to information theory, more of like an applied philosophical point of view. I was interested in the epistemic interpretation that you were talking about. If you take an epistemic interpretation, you were talking about non-compositional states which can't be decomposed. So if you do accept the epistemic interpretation, does this force you to accept a model of non-compositional actual information that you're representing with this quantum information. Would that be how the epistemic model worked? Yeah, or not?
Yeah.
Okay.
Thank you for the advice. Yeah.
Interesting. Okay, thank you. That has interesting implications then. That's very interesting. Thank you. Okay.
Thank you.